Alright, so let's look at some examples finding indefinite integrals involving the natural logarithmic function. So the first one, the integral of 15 over x dx. So first thing we want to do is pull our constant out of this integral. So this is 15 times the integral 1 over x dx. And in this case, we have no substitution that we need to do. So we know if it's the integral 1 over x dx, then we know this is going to equal to 15 times the natural log absolute value of x plus c. And we're done with that one. So now you know what's coming. You check your answer. All right, for the second one, so the integral of 1 over x minus 5 dx. So think 1 over u du, right? So u here is equal to our denominator. So u is x minus 5. So du equals dx, or 1 dx. And notice we have the 1 dx left over. So then this is equal to, so the integral of 1 over x minus 5 dx is equal to the integral 1 over u du. And so that is natural log absolute value of u plus c. So it's natural log absolute value of x minus 5 plus c. We have to leave the absolute value here because we don't know if x minus 5 could be positive or negative, because x could go from negative infinity to 5 union 5 to infinity, right? The only value that x couldn't equal is 5. So we have to have that natural log, the absolute value on the natural log. And of course, as always, you should check it to make sure, right? So check by taking the derivative. Whenever you do that, just ignore the absolute value. I'll do one on the next one. All right, so C, the integral of x squared over 5 minus x cubed. So same idea, right? So u we're typically going to let be our denominator in this case, so 5 minus x cubed. So again, we're thinking 1 over u du, right? Or u to the negative first du, right? So u equals 5 minus x cubed. Du equals negative 3x squared dx. Uh-oh, these don't match, right? So how can we make these match? So if we have x squared dx, but we have negative 3x squared dx equals du, so we got to turn that negative 3 in front of the x squared into a 1. So divide by negative 3 on both sides. So negative 1/3 du equals x squared dx. So our integrand then is going to become negative 1/3 times the integral of 1 over u du. So that's negative 1/3 natural log absolute value of u plus c, which becomes negative 1/3 natural log, when we do our back substitution, absolute value 5 minus x cubed plus c. So let's check this. So to check these, we're going to drop the absolute value symbol. So we want to find negative 1/3 natural log of 5 minus x cubed plus c prime. So that's going to be negative 1/3 times 1 over blah, so 1 over 5 minus x cubed, times the derivative of the blah, so times negative 3x squared, plus 0 for the plus c's derivative. And so we end up with negative 3x squared over times a negative 1 over positive 3 times 5 minus x cubed. So the 3's cancel. Negative times negative becomes positive. And so we're left with x squared over 5 minus x cubed, which is our original integrand. So we're good. Alright, so example 1D, we're still finding the indefinite integral and checking our answers. So for D, we've got the integral of 1 over x minus 5 squared dx. Now, a bad habit to get into is just seeing 1 over something and automatically assuming that it's going to be a natural log. But remember, it all depends on the exponent on u, right? So in this case, we let u equal x minus 5. Du equals 1 dx, right? So we're good, it matches. But then this is the integral of 1 over u squared du. So notice our exponent is not a 1. So it's not just 1 over u, right? It's 1 over u squared. So in this case, we have to rewrite this. So this becomes the integral of u to the negative second du. And then we're going to use the power rule for it. So this becomes u to the negative first over negative 1 plus c, which then just becomes negative 1 over u plus c, which is negative 1 over x minus 5 plus c. And then you check it. But notice looking at it, so what's the difference between this one and b that we did? So on this one, we had integral 1 over x minus 5 to the second power dx. But on b, we had the integral 1 over x minus 5. So notice here, this was just 1 over the blah, right? And we ended up with the integral of 1 over u du. And so we ended up with a natural log. But on the one we just did, d, because we ended up not with 1 over u, but we ended up with 1 over u squared du. So that's how we know we have to use the power rule. And we're not going to end up, in this case, with a natural log. We end up with an algebraic linear function. So the same substitution was used, but we did not use the same integration formula because our exponents were different in b and d. All right, let's look at e. So the integral of x squared plus 3x plus 4 over x minus 5. So the first thing we need to do before we can do this is we need to do long division. So anytime your power on your numerator is larger than the power of the denominator, you want to do long division first to be able to rewrite and simplify our integrand. So let's do the long division. So if we look at it, x squared plus 3x plus 4 divided by x minus 5. So thinking about long division, x times what's going to give us x squared? So x. So x times x gives us x squared. X times negative 5 gives us minus 5x. And then we're subtracting that. So x squared minus x squared is 0. 3x minus negative 5x. So that's 3x plus 5x gives us 8x. Bring down our 4. And we keep going. So same method of thinking. So x times what gives us 8x? So positive 8 will, right? So 8 times x gives us 8x. 8 times negative 5 gives us negative 40. And we're subtracting again. So 8x minus 8x is 0. And 4 minus negative 40 is positive 44. So what happens is we can then, using this long division that we just did, we know that x squared plus 3x plus 4 over x minus 5 is equal to our quotient, x plus the integral, in this case of x plus 8, plus our remainder. So remember, when you're doing the long division, you stop when you end up with a degree that's left over lower than the degree of your divisor. In this case, it was x to the first power, and 44 is a constant. So plus 44, our remainder, over the divisor. So over x minus 5 dx. So you'll always be able to rewrite the integrand if the numerator is larger, the degree of the numerator is larger than the degree of the denominator. And so now, if we integrate piecewise, right, so split it up into two separate integrals. So the integral of x plus 8 dx, we know that's going to be a piece of cake, right? It's algebraic, pretty easy to do. Plus the integral of 44 over x minus 5 dx. So first one's a piece of cake. So integral of x plus 8 becomes x squared over 2 plus 8x. Plus the integral of, we still got 44 over x minus 5 dx. B was pretty much exactly like this, very similar. So I'm going to leave the work to you looking at B. And you end up with x squared over 2 plus 8x. Plus you end up with 44 natural log absolute value of x minus 5 plus c. And then, of course, as always, you check it. All right, so f, we have the integral of x squared plus 4x over x cubed plus 6x squared plus 5. So in this case, our denominator has a larger power, so we can't do long division. So think u is our denominator, so u equals x cubed plus 6x squared plus 5. Du equals 3x squared plus 12x. And so du over dx. So then du is 3 times, so factoring out, right, 3 times x squared plus 4x dx, right? So notice we have an x squared plus 4x dx, and then du is 3 times x squared plus 4x dx, so we got to get rid of that 3. So 1/3 du equals x squared plus 4x dx. And now we're good, so we end up with 1/3 the integral of 1 over u du. So 1/3 natural log absolute value of u plus c. So 1/3 natural log absolute value of x cubed plus 6x squared plus 5 plus c. And then as always, you should check this, right? All right, g. So we have the integral of ln x to the third power over x dx. So here, we do have a 1 over x dx, but what's going to happen? So if we were to let u equal 1 over x dx, so let u equal 1 over x, then du is going to be, du dx is going to be negative 1 over x squared, right? So that doesn't help us. That doesn't get rid of our natural log of x to the third power dx. So that's not going to work. But what do we know? So think again about the relationship between natural log x and its derivative, right? So if we let u equal natural log x, then du over dx is 1 over x. So du equals 1 over x dx. So looking at this integrand, then, this becomes the integral of, if we think about it this way, natural log of x to the third power times 1 over x dx, right? So rewriting it like that. Now, that matches what we have, right? So this just becomes the integral of u to the third du. So u to the fourth over 4 plus c. So 1/4 natural log of x to the fourth power plus c is this antiderivative. And so let's check this one. So if we check it, so we have 1/4 natural log of x to the 4th power plus c prime. Then, so 1/4 times 4 natural log x to the 3rd power, right? Times the derivative of natural log x, which is 1 over x, plus the derivative of c, which is 0, using the chain rule in that first half. So 1/4 times 4 cancel each other out, so we end up with natural log x to the 3rd power over x, which is our original integrand, and so our work checks out and we're good to go. All right, part H. So the integral of e to the 2x tangent e to the 2x dx. So first off, don't try to rewrite this, right? So instead think the integral of tangent u du, right? So tangent of blah, right? So then if we let u equal the blah inside of tangent, so the argument of the tangent function, e to the 2x, then du dx is equal to e to the 2x times 2, right? Using the chain rule. So chain, right? You're using the chain rule. So du equals 2e to the 2x dx. Well, we have 1e to the 2x dx, so we got to divide by 2 on both sides. So 1/2 du equals e to the 2x dx. Now it matches. We're good. So this becomes the integral of 1/2, and that 1/2, remember, can be inside or outside of the integral. So 1/2 integral of tangent u du. And so now this is one of our formulas. And so if you forget the formula for tangent, you can always rewrite it as sine u over cosine u, and then use the logarithmic derivative to work it out using the u sub there. But I recommend just memorizing the formulas. It's not that bad of a formula to memorize. So we have 1/2 times the antiderivative of tangent u is negative natural log absolute value of cosine u plus c. So we end up with negative 1/2 natural log absolute value cosine u. So bringing that 1/2 in, multiplying that by the negative 1 plus c. So negative 1/2, doing our back substitution now. We have negative 1/2 natural log absolute value cosine of e to the 2x plus c. So let's check this one. So we had negative 1/2 natural log absolute value, and we'll drop the absolute value for purposes of checking. So we have negative 1/2 natural log of cosine e to the 2x plus c, and it's going to be prime. So using the chain rule, right? Then, so this is negative 1/2 times 1 over cosine e to the 2x for the natural log of blah. Remember, derivative of natural log of blah is 1 over blah times the derivative of the blah. So now times the derivative of cosine e to the 2x, which is going to be, derivative of cosine is negative sine. So negative sine of blah, negative sine e to the 2x. But be careful, we're not done, right? Now we got to multiply by the derivative of that blah, because we're doing another chain rule here. So times the derivative of e to the 2x, which is 2e to the 2x. And then from here it's just a whole, and then plus the derivative of c is 0, since c is a constant. And so then cleaning up, we've got the 2 and the 1/2 cancel. And the negative and negative become positive. So we're left with sine of e to the 2x times e to the 2x over cosine of e to the 2x. And remember, sine over cosine is tangent, so we're left with e to the 2x times tangent of e to the 2x. And that was our original antiderivative, so it checks out. Alright, so let's do one more example of a indefinite integral. So let's look at the integral of secant of x over 2 dx. So the function you should be thinking of, think secant of blah, right? Secant u du. So u is equal to x over 2, or u is equal to 1/2 x. So du dx is equal to just 1/2. So we have du is 1/2 dx, but we only have 1 dx in our integrand. So we've got to make 1/2 turn into 1. So to do that, multiply by 2 on both sides. So 2 du equals dx. So now we can rewrite this as 2 times the integral secant u du. So we know the antiderivative of secant of u du is natural log absolute value of secant u plus tangent u plus c. And then do our back substitution. So we start in x, we need to end in x. So u was x over 2. So we end up with 2 natural log absolute value secant of x over 2 plus tangent of x over 2 plus c. And so now make sure that you go back and check.